Welcome everyone to today's video where we will learn about properly conducting a spectrophotometry experiment.
Spectroscopy is the study of how light interacts with matter, and today we will be using a spectrophotometer to study how much light different substances absorb.
To determine the amount of light a substance can absorb, you load a sample into the spectrophotometer where it can be analyzed. The machine contains a special light bulb that can emit precise wavelengths of light, and on the other side of the light bulb sits a detector which detects any wavelengths of light that reach it. So when we set a sample in between the two and run the machine, we can see which wavelengths of light made it through the sample and hit the detector versus those that were blocked by the sample to determine how much light the sample absorbed.
The samples you put into the spectrophotometer must be contained in a small plastic container known as the cuvette. So before you scan anything, make sure your sample has been transferred to a cuvette.
Make sure not to overfill your cuvettes because spilling any liquids around the spectrophotometer can be a costly mistake. To ensure that there is enough sample for scanning, but not enough to cause spillover, we recommend filling up the cuvette 75% of the way.
Just like when you use an electric balance in the lab, a spectrophotometer must also be zeroed out before use. To do so, load a cleaned cuvette only containing water into the machine and click the zero button on your screen. Afterwards, remove the blank sample in preparation for your solutions.
You are almost ready to begin scanning your prepared samples, but first you must check the spectrophotometer settings to ensure that you are scanning across all wavelengths. For this experiment, you're analyzing solutions with an unknown absorbance value and unknown absorbance range, so scanning across all wavelengths ensures that we don't miss any potential peaks of wavelength absorption. When scanning similar solutions like we are in today's lab, you can check each solution's absorption peaks to see if they match, thereby indicating that each solution is relatively pure.
A second reason as to why you should always scan across all wavelengths is that it easily allows us to view the wavelength peaks and identify the solution's lambda max value.
If you didn't already know, the lambda max value is the wavelength at which a substance absorbs the most light. We will be using the lambda max value to help us scan our solutions properly and to get an accurate absorption value.
Now you are ready to begin scanning your prepared samples in the machine. To make sure the spectrophotometer has a clear reading, always wipe down the sides of your cuvette to remove any fingerprints or other obstructing marks.
After cleaning, carefully lower the cuvette containing your sample into the machine and ensure that the clean sides are facing the light bulb and the detector. Afterwards, make sure to close the spectrophotometer's lid.
Now go back to the computer and press the read button on screen. The sample's absorbance value should appear in red at the top left corner of the screen.
Make sure to write the absorbance value down, as you will need it for any later calculations.
Now that you have successfully scanned your sample, go and carefully remove it from the machine. And as always, make sure to shut the spectrophotometer's lid after you are done.
With your newly acquired absorbance data, many other scientific concepts can be explored, such as the relationship between concentration and absorbance seen here.
Because concentration and absorbance have a linear relationship, you can use the Beer-Lambert law to calculate a solution's concentration once you find its absorbance values.
The equation consists of four variables which are as follows. First, there is the absorbance variable represented by an A in the equation. The absorbance is determined by the spectrophotometer, which is why zeroing the spectrophotometer before use is so important. Zeroing it out allows you to cancel out any previous absorbance filters so that your results are without interference. The next variable is the epsilon variable, pictured as a stylized E. It represents the absorbance coefficient of your solution, which in this case is the slope of the line seen in the previous absorbance versus concentration graph. Next is the C variable, which represents concentration. It can either be determined beforehand or solved for algebraically once you have the values of the equation's other three variables. Finally, there is the length variable, represented by a lowercase l, which is the distance that the light had to pass inside the spectrophotometer. In our case, this is the width of the cuvette, which is 1 centimeter.
Congrats on completing this week's lab, but before you pack up and leave, you must clean up your lab space and dispose of the reagents you used.
For this experiment, you can simply wipe down your lab bench with a damp paper towel.
After that, make sure to properly dispose of any excess reagents or solutions. For the substances used in today's lab, it is okay to pour them down the sink.
Thanks for watching, and we hope you had an amazing lab experience.